can explain in different fashion. You have not understood? Hmm? You? Hmm? So what is happening? You have sun's position somewhere here, and you have plane like this, horizontal plane like this. And this is east-west, and this is sloping north-south. Correct? Position is like this, and that is north. So as it comes from, because position will be, depending on the season, can shift from this axis to this axis. So as it slopes, at horizontal you get certain energy. As it goes on increasing, it will happen in such a fashion that as it increases this 50-degree slope from horizontal, then this land will come under mountain shadow. So you can do that. So how much energy coming will vary. So you can see here from this graph that amount of energy coming on any surface will be a function of its latitude, longitude, its time of the day, time of the season, and slope angle, slope orientation. So because of that, if you go back, that there will be, you require this plug into this equation, solar radiation index. Convert this into, depending upon these parameters, convert into solar radiation index. And then you get, that is why it is index is in that sense important. Right? Then next thing is, how do we estimate? Because we are not using that thing. Suppose once we got the melt factor, we got the temperature, and temperature is not available throughout the basin. It is available only one or two places, or maybe only one place. From there, now we want to extrapolate that temperature in different altitude zones. So what you will do is, you require temperature index at different altitude zone. Not only, you need temperature, convert it into temperature index. So the altitude adjacent temperature index, you can use the temperature lapse rate, mean elevation at station, and mean elevation. By using simple relationship, you can calculate. You will do those calculations later on to do that. So using this relationship, you can know what will be the change in lapse rate in a different altitude of basin. So what we did until now? So what we did is, we are still working on melt factor, or we are still working on melt, idea of melt. How much melt is produced? Correct? We are only working on that idea. We have not yet shift. And there are a lot of things you can do to know how much melt is there. Something is available, something is not available. And then what you need is TA, temperature index at various altitude, is the T temperature index at meteorological station plus H. So you use this relationship to know at each altitude zone. So as we have discussed, if TA is negative, it is considered 0 in model, and this will give you melt for a unit area. Correct? You understand? This is not giving you melt for entire basin. It is giving you melt for a unit area. So what you do, next step for you is to get how much it will melt for entire basin. Correct? How much it will we know each altitude zone, how much may melt, how many cubic centimeter, or if you want to convert it into mass, you can convert it into mass. Per unit area, how much snow is melted, you can calculate that. In order to know now, spread it for the basin, because it is not melting one place. We want runoff for entire basin, and basin is a special entity. It is not, so in order to do that, how much, what we need to know is how to estimate model melt for a basin. That is the idea, that how much is the basin area in each altitude zone. We need to understand that. And then how much is the snow and glacial cover area in each altitude. Understood? Huh? Any confusion here, this side? Huh? And how we will ensure that amount of meltwater produced is not more than total water stored in each altitude zone. What is possible is, suppose you have 1 meter snowfall in winter, correct, and you have one altitude zone. As summer comes, your model will show melt is, you have positive degree days, and you will produce melt if there is no snow. Right? What your model production of melt really in physically means nothing. So how we will constrain model to ensure that they are not producing runoff more than what it has actually has. And that brings very tricky issue, because we will look into that, because that is where there is a subtle difference between this you have seen. The first thing, we will issue that problem later on, but next thing is how much is the snow in each basin we want to know. We have to know that NDSI method can be used. We have NDSI method by which we will know the snow. We can use the SITM data, which is easily available, and you can get the area altitude distribution, and you can plot the graph like this hypsograph. You can plot the graph, and there is no issue. Is there any issue on this? Everybody understood this graph. That is just giving you, so both the parameters you can get it. Then you superimpose on it like this, that either you can automatic technique, you can do manual, whatever you want. You can superimpose it and get the area under seasonal snow in each altitude zone, right? Now, the key question is, how we will ensure that amount of meltwater produced not more than total stored in each altitude zone. There could be different solution for this problem depending upon what kind of data you are having. Suppose you have decent data on snowfall in the basin. You can simply constrain model such a way that, suppose you know that in this altitude zone we have 1 meter of snowfall, correct? So you will say that in this altitude, if amount of melt is more than 1 meter, it should be treated as 0. So likewise, we can constrain that model. There is no big issue on that. But if you don't have that data, like you have a huge basin, like say Satluj or Indus, where most of the area is outside Indian territory, and you don't have any data. So what you will do? The engineers are very smart people. They have also devised way of doing it. So what you should do is, you develop this depletion curve, right? You know the depletion curve meaning. That means how, as you move from here, how this is, snow cover is reduced in each altitude zone. So this is percentage of snow cover in each altitude zone, how it is reduced with time. and you plug it into the model, and you will know. And if you have data for 10 years, 20 years, 30 years, like that, then you will know how much water is produced from this altitude zone. So some way you can constrain it so that you will be able to say that, and then you still fulfill the principle of conservation of mass, which says that you cannot produce the more mass than what it exists. So there are different ways you can do it. So there are certain well-known models where they do all these things. Is snow melt runoff model, SRM, which I talk about, Martinic and other, Rango. So this is where they are using the degree day approach. They use the seasonal snow cover, and model parameters are temperature, snowfall, and snow cover area. And other parameters are required in that model, which can be generated by, but we will not go into detail of this model. Just I am giving you this model exists. And however, for seasonal runoff model uses depletion curve. Depletion curve and runoff are used to assess snow reserve for seasonal runoff. Such models are difficult to use for glaciated region, which shows no large depletion due to runoff. This is an old model. Now they have modified it. But when I was developing model way back in late 90s, this model was then not updated. Now it is updated. What is the idea of this last sentence? Can you read it? Such models are difficult to use glaciated region, which shows no large depletion due to runoff. Some way you are right. Can there be simpler explanation? See, if you look into the sentence ahead, earlier this, the seasonal runoff model uses a depletion curve. That means in order to produce the runoff, snow area has to retreat. And if snow area has to retreat, if glaciers are melting, they are not retreating on seasonal basis. They may be retreating on long-term basis, not on seasonal basis. So, because originally that Rango's model was developed for a region which has no data. Therefore, they rely production of runoff based upon the depletion curve. So, this is amount of land is depleted, this much amount of runoff came. But moment you go to the glaciated area, there is no depletion of land. And remember, glaciated terrain has an inverse relationship than the snow region. What it means? Suppose you have a high snowfall in a basin which is not at all glaciated, it is only seasonal snow. High snowfall, you will get large runoff because that is going to melt in summer. If that is the situation in glaciated terrain, you will get the less runoff. Why is that? Yeah, that is because glaciers will be covered by seasonal snow for longer period, and the albedo of seasonal snow is much higher compared to the ice, and so less energy is absorbed. But if you move and you take highly glaciated terrain in Parvati Basin like Tosh and others, you will realize that inversion relationship is very powerful. Or if you go near glacier and major runoff, you will realize if the year you have a large snowfall, you have positive mass balance and less runoff. If you have less snowfall, you have more negative mass balance and you have more runoff. So these differences has to be understood when you start developing this model. And that is why when earlier phases, Rongho's model was not extensively used for glaciated terrain, but subsequently it was modified. There are some corrections were made now on that. So now you forget about any commercially available software or anything. Now somebody has given you a problem and asked you to solve this problem. This is a real problem which is posed to me, and then you need to find a solution which satisfies the planners. So what is the question? Question was, they were at that time, everybody was excited to have hydropower stations in Himalayas. It was in mid-90s we are talking. And Himalaya, they were arguing that it's a large number of snow and glaciated streams. Systematic assessment of hydropower potential for each stream is needed. Suppose you have 5,000 streams in Himachal Pradesh. They want to know how much is the power potential for each stream. Why this is important? Because this power potential is not developed by state government. It is developed by private parties. So if some basin has 100 megawatt power potential, somebody has to invest 1,000 crores in it. Do that company has a capacity to invest that money or not? So there is a policy decision has to be followed. So we require systematic then. Another key problem is, in mountain stream has a lean discharge in winter, and feasibility of hydropower plant depends on winter discharge. So can you give us the better estimate of winter discharge? They will say, don't bother for summer, because you have 4 turbines. All 4 turbines will be functional in summertime when monsoon comes in, but they doesn't operate in winter time. They can run only one time. So only 1 turbine. So we have a 6-month time when only 1 turbine is operational. Your commercial feasibility is in trouble. So they want to know better estimate of winter. Therefore, you need to develop a model which can assess interseasonal variability. At this stage of planning, you are not interested in knowing how stream runoff will change every day. That will come at the operational phase of plan. At this stage of planning, it's only state government sitting in office want to take certain policy decisions. So you understood? So this is problem which needs to address. And another problem is how electricity regulator operates. That they operate because they have to do power purchase agreement in month of February for next summer. So can you tell us, that is argument in February, how much power we will generate in summer? So they can have a better estimate of, and they can promise appropriate power, and there is no penalty on them for that season. So these are the policy and commercial decisions. So now you look in terms of any model, like say Martinique. This is the problem. Martinique and Rango model, which is using for large region, and which is sometimes there are glaciers present in those regions, may not help you to address this problem, maybe now. And then of course this problem I asked myself, not that state government was interested in it, but my problem is how climatic variation can change glaciers, snowfield, and how these changes will affect future stream runoff and future generation. Because scientists can only inspire if there is a science. No, we are not interested in solving commercial issues. We should do that, but it doesn't give you a kick to do it. So after they completed asking their scientific question, commercial question, I asked myself another scientific question, so that I can, so we can work on it. So let us, in this context in mind, we look at. So now this is time for us to break that scientific question, that managerial question, into certain scientific way of doing it. So first thing, when these questions were raised, first thing you need to know is, what you want to do is how seasonal, how runoff will change in a seasons. In autumn, winter, summer, and monsoon, and this is published in paper in 2002, and probably you will get that paper, and you have to read it carefully before solving the exercise which we are given to you. So this is this paper. So key question converted to winter, summer, and monsoon. But what is this winter, summer, and monsoon? How do you know when winter starts, when winter ends? How summer starts, when summer ends? What are the scientific principles on which we will say this thing? Because you can't arbitrarily decide that this is the winter, this is the thing. So we will just look at this. This was the original model which we thought that what is the equation of that model. We will elaborate that later on, not now. So then key question is how this changes. What you do is, what we did at that time is we plotted the hydrograph of small streams. That is a Malana. If many of you have gone from Manikaran, how many of you have gone to Manikaran? Yeah, okay. So before that, there is a Malana village, and there is a beautiful, that is a very beautiful place. So there is a stream which is called Malana Nala, and there was a runoff for that. So we plotted that Nala, or we plotted that runoff, and say that when, depending upon the hydrograph, we thought that this is a possible way when there is an increase in runoff from winter, then it's like that. In the monsoon, when there is a sudden increase in runoff, then monsoon arrives, then autumn, and then when it really collapses, winter. So depending upon the stream runoff. Now remember, this thing will change year to year, and also remember, it will change region to region. We were very naive at that time, so we didn't realize that, but I'm not tinkering with that right now for you, but you need to, there's a scope to put more on scientific basis to do this thing, and it will vary from region to region. That realization also has to be there. So now, let me explain this equation. Before that, we will be heading towards different thing. So what you do is, this is what we thought. We can write the model. So model in this is Q. What is the average seasonal runoff, which is in cubic meter per second. Right? Is that clear? It is not total volume. It is cubic meter. It has fundamentally three characteristics. One is how much it is melting from seasonal snow, area of seasonal snow, then area of seasonal snow and glaciers. It uses area of seasonal snow. So eventually, when snow line retreat is higher, it will only consider glacier area and snow line area will go on. The winter snow melt, snow cover in winter, average seasonal rainfall, and B is the basin area without snow and glacier. Probably it hardly makes any sense for you, because these are just symbols and words. But when you actually start doing this exercise in afternoon, you will feel what it means. The idea of this modeling is this. You start modeling in winter. So you have a winter runoff, winter melt. Correct? Then you move for summer. And in summer you have, this model assumes most of the runoff is coming from snow melt. So you know at the end of winter how much water equivalent in each altitude zone is left after winter melt. Then you move on to monsoon, which is a different ball game, and then you move on to autumn, which is predominantly melt is coming because of the glacier melt and seasonal snow melt. And then winter, which is mostly coming from snow melt. That is maybe valid only for this region, lower altitude of Himalaya, and need not be valid for all regions of Himalaya. That is how it was done. So now you get the daily rainfall data, because there are no, actually at that time there was no runoff data, rainfall, snowfall data was available. So we have data at large G for 5 years, and it was average snowfall is estimated from there. We get the daily average rainfall was estimated. In addition to that, Bhakra BF Management Board manages large amount of snowfall stations. There are 20 stations, and we have taken data from 76 to 87, 88, and we got the mean winter snowfall. We don't want to work now on annual variation in this model, but this model gives you long-term season, because we are addressing first problem, which is having a systematic estimation of hydropower potential for all streams in Himachal Pradesh. That problem we are looking now. We are not looking into second problem, for which we have not written model and we have not attempted also. So some of you can try do that. So now there are no other data, so we have fixed these values where you can keep on changing. One of the way to get melt factor, which is Rango and others, are using 1.1 divided by density of snow and density of water. And these are the figures which thought, depending upon glacial altitude in summer, snow melt in monsoon, melt factor in autumn and winter and snow. So that is how we thought we can use this figure. And now third component is how much is produced. After that, how much of that enter into the stream runoff. Remember, this is the only parameter available for you to adjust your runoff. So it's varying from 0.6 to, why there are so many things here. Like glacial melt in summer, seasonal snow cover in summer, glacial melt in monsoon, because there are 4 different programs. Correct? For winter, different program, for it's not, because at that time, when I wrote that program, original program was on QBasic. Because I was not very good in computer programming, but I learned the QBasic and wrote that program in QBasic in 90s. Subsequently, our students have done C++ and numerous others. It's now powerful, is done. So you can use that and get, and then subsequently Fortran also we did do that. Now, when you run this model, you can see that how it compares with the field, actual values. That is what it is all about. And you can see here in autumn is a Malana Nala. Model is 10.2 and field is 9.9, error is given. Then what we did is, after development of this model, we installed this model on computer of Himachal Pradesh Electricity Board. Because the ISRO people say that, okay, fine, you may say it is great, somebody has to use it. So they have verified it for Tosh Nala, for which they had a stream runoff. So one of their engineers came and worked with us for 2 months to understand this model. And they did on their own at Simla, and they got the variation, which is very high in monsoon, which is at 25%. We also have 18, 19%. But they are very good in autumn, winter, and summer. And subsequently, it was applied to numerous bases where there was no stream data was available. And they estimated this for Sorangad and Kirangad, these are two bases. And from here you can estimate power potential. How you will estimate power potential from here? Correct. No, you got this runoff now. Now how you will estimate power potential of stream? Simple, yeah. Multiply by? This is only runoff. We are not cubic meter per second. That is not the unit of power. Now, how you will convert this runoff into power potential of stream? No, that is not the question. Question is, I want to know in autumn how much is power potential of Sorangad. There is one more thing you require. Have any one of you have seen the universal power equation? No? Have you anyone see the power station? Huh? So what they do? They take water from somewhere, and where are turbines? Down. You required a head. That is called head. That means how much is the difference between your take in and outlet, and that head you need. I thought you multiply by head and simply you get the power potential. Now key question is that, okay, all right, this is done. Now next question is, suppose this model is ideal and fine and we did it. How we are going to do it to estimate? How to estimate change in runoff due to climate change? How it will change and how it will affect the power potential. So this is paper which also you will get it when you are, I don't know whether that is an exercise or not, but you can download always. This is with me and Rathod and other people have done. How to estimate change in runoff due to climate change, right? Now, what are the things likely to change? First thing is, most probably it will change, is certain region where there is lower altitude, where there is a snow, it may convert into rain, right? What is also possible for you is certain time some amount of snow can melt in winter itself. even if it is taken place. So what you do is, suppose you take the situation where this is the simplest thing to do, it's not very big idea to do, that you can have change in snow cover due to rise in temperature by 1 degree Celsius. Presume there is a 1 degree rise in temperature. So this is area altitude distribution of basin, correct? Then this is present area altitude distribution of snow cover. Clear? Now, by 1 degree rise in temperature, you just add the lapse rate, and you got the new change in area altitude distribution. So you will get the idea of how snow is going to change. But there is a bit complication when you want to say how glacier area will change. And there you need to apply some glacial dynamic principle. So what we did is, suppose this is, in case of glacier, this is area altitude distribution of glaciers. Right? This is how glaciers are distributed in this basin. And this is what equilibrium line altitude is of today. Right? You got it by using series of satellite data, and we have discussed quite extensively how to estimate ELA. We have estimated. Now, as we are arguing earlier, ELA is also nothing but the 0 degree isotherm. So 1 degree rise in temperature will move ELA upward like this by using simple lapse rate. Nothing big you did, you just added a simple lapse rate into that. And you got the new AR, and the change in AR will take place from 0.37, which is of today, to 0.17 due to 1 degree rise in temperature. Now what do you do with that? It will change the mass balance of glacier. So you will know how much mass balance is there. Now I don't know whether I have, okay. Now it brings you a slightly different concept. You need to apply the glacial dynamics into it. What it means is, if you simplify this equation of continuity and glacial dynamic equation, you can rewrite that equation as written by Patterson is change in terminus length of glacier is equivalent to datum length. You can take approximately datum. Datum length in theory means what would the length of glacier when glaciers are at equilibrium. But in this case, we have approximated that it is of length of today. What is the length as of now? Now what else you can do is a B. Remember, B is not a mass balance. B is decrease and increase in mass balance. That means change in mass balance you are adding. So you are not giving absolute value, change in mass balance. And A0 is ablation rate of terminus. What is the meaning of why this term has to come? No. No, EL is moving upward, it is changing mass. And because of change in mass, glaciers are responding, retreating, correct? Because there is a, as you know, that how much the further flow of ice will function upon amount of volume which is ice available in upstream. That you have calculated by using various equations which Helge has given. A0 is because it's quite possible that glacier may be losing its mass, and enough ice is not pushed into the downstream, but retreat will depend upon ability of nature to clear snow at the lower altitude or clear ice at lower altitude. If terminus is heavily covered by debris, that land will not be cleared by glaciers. It will remain there, ice can remain there for very long period because of a thick debris cover. That is compensated, we can't use any other, that is compensated by ablation rate of terminus. So depending upon debris cover, ablation rate of terminus can change from glacier to glacier. And then another key problem is how much response time, how many years it is going to take. Right? Will it happen in 2 years? That means if glacial mass is changing, as in earlier equation we said 0.37 to 0.17, and how long it will take glacier to complete the cycle and come to the steady state condition again. That means its length, its relationship between the length and mass balance becomes equal. That means that 0.17 eventually has to change the AR such a fashion that it will become 0 or something like that. So that changes how many years it will take. That is defined by response, response time. So it is function of maximum thickness and annual ablation of terminus. This is a classical paper, I think way back in 2004, no, earlier, around 2000, in published in Journal of Glaciology, where there is a complete solution for this equation is there. It starts from the basic equation, how he arrived to this equation, but you can pick up just this for this purpose and say that it's function of two maximum thickness. Remember, this is not mean thickness. There's a difference between mean thickness and maximum thickness. And then is annual rate of terminus, melting rate of terminus. If you apply this thing into the model, what you will have? What you will, if you have that so many, so let us take in terms of the glacial extent first, snow extent. We have this, anyway, it doesn't matter if the winter, summer and autumn. We have approximately 40 square kilometer area of a glacier in which is Sorangad basin, and if there is a 1 degree rise in temperature, its aerial extent will reduce to 16.4. Right? We have not said how long it will take, but you can do it because we thought that we will only predict when the effect of 1 degree Celsius is finally, arrive at that time. And the average snow line will change in various seasons from 3,979 to 4,001. 140. Likewise, you can calculate for all seasons. And also you can calculate how snow extent will change. And this is for 2040. So you can also know that. And then temperature index will change from year to year. You can calculate that. And after that, you will know how much stream runoff will change due to 1 degree rise in temperature. right? Hmm. Once, so it is in autumn it is a 20% reduction, in winter it is 18%, in summer it is 8%, and in monsoon it is 28%. Key question is, key question is why there is a large variation in monsoon. Even then, even though we have not changed in model amount of rainfall. Right? Model, when this paper is published, you can do it now because there is a lot of good data available in these days. And field is still open for everyone to work. You can see 28. This is possibly because even though since there is a substantial reduction in areal extent of glaciers, if you have seen, it's taking from 40 to 16 square kilometer. So it is approximately, yesterday Helgi was talking about, there will be 10 to 15% if there is a rain on ice, there is 10 to 15% approximately in increase in melt take place. And this region you have very high, because it's very low altitude basin. This is the first basin as you move from south to north. Parvati is the first glaciarized basin, where the temperature of rain is also very high, and there is a huge amount of rain takes place in these basins. And because of that, some of the reduction in monsoon is coming because of the lack of contribution from glaciers. And you can see other seasons where, like summer, is predominantly coming from seasonal snow. And so in this way, you have a handle on what processes are taking place in the mountain and how much impact each processes will have. That you can do it. And autumn is also, because it is significantly dominated by glacier melt, is also going to change. Not much in summer, and also not much in winter also, but it is going to reduce anyway in winter too. I was expecting that it will go in winter, but it has not come out. And this is just, you can see that how it's error in model for this Vangargarh basin, where you have a huge data. And it's really not much. It's from 5% to 3.5%. It's really good. So what we will do now is, if there are no questions, or if there are questions we can take, otherwise we will break for 10 minutes, have a cup of tea, and you can start your exercise. I am sure you will be, they have already emailed exercise? Okay. You can download. Some who don't have that, we can, it's only one page, isn't it? Okay, all right. So question paper you will get, but the data you will get by email, because there is an Excel file for data. And just I will brief you 5 minutes, but I will not elaborate how you will do it. I want you to read a 2007 paper and then do it. It has two purposes. One purpose is to make you read, and another purpose for me, how to rewrite papers so many people can understand. So wherever you don't understand, it will help me changing next time. Okay. What is, okay, sorry. Okay. What is given to you uh, is, is given winter seasonal time period. If it is not here, you can read into paper, but most probably it is here. It is given there, no? Okay, it is given there. The temperature data at Bhuntar is given for you. That is in Excel sheet, right? And at its altitude is 1067 meter above sea level. The area altitude distribution of seasonal snow. Seasonal snow is given. Melt factor of snow in winter is given to you. Then mean snow line altitude is given. Right? Is there in this? No, is there? There's a table, mean snow line altitude table is there. It is there, and the PDF is paper is published to you. Now you need to read that paper, spend some time, and then what you need to do is estimate snow cover in each altitude zone, winter degree days in each altitude zone, cumulative degree days for winter. Then melt of snow in each altitude zone using melt factor. Correct? It's very simple. Volume of snow melt in each zone. Right? This is a unit, this is over a unit area, this is over a geographical area. Cumulative volume of snow melt. How much is total? Total runoff in Qmax after applying runoff coefficient in winter. That's it. This is very simple exercise, and this is equation. You just keep eye on it, and that's all. So I will leave this for you if anyone want to refer it. Read paper, think over it. It's very simple, provided you spend quality time on this problem.
place, and somehow, and then into the rivers, and that's all. But in some cases, the water may be accumulated in the glacier, not moving as we all the time, as we talked about yesterday, but accumulating into sometimes subglacial lakes. There can also be lakes on the surface of the glaciers, and there can be lakes in front of the glaciers, which are the most common type here in the Himalayas. And we can classify or distinguish between several types of lakes. We can have subglacial lakes. They are, as the name is telling you, located underneath the glacier. They can be located in depressions in the ground, and this is the case for many of the lakes in Antarctica, which I mentioned to you yesterday. Yesterday I mentioned that 124 lakes have been detected by are a very great hazard here in the Himalayan mountains, but also in Iceland, where I've been working on outburst floods like that. And here in the literature in India, it's often called GLOFs, G-L-O-F, GLOF. And we have a special name in Iceland for this. This is Jökullaup. But anyway, what this means is a sudden outburst of water. Yesterday we talked about how water is transported through a glacier, and typically it's moving rather fast down to the base and along the base, and somehow, and then into the rivers, and that's all. But in some cases, the water may be accumulated in the glacier, not moving as we all the time, as we talked about yesterday, but accumulating into sometimes subglacial lakes. There can also be lakes on the surface of the glaciers, and there can be lakes in front of the glaciers, which are the most common type here in the Himalayas. And we can classify or distinguish between several types of lakes. We can have subglacial lakes. They are, as the name is telling you, located underneath the glacier. They can be located in depressions.
For example,
ground, and this is the case.
you can use a crane in which you can mount a camera and look at something.
Which I mentioned to
You can use an aircraft,
yesterday.
that's fairly commonly used, or you can use a balloon. But the focus of this lecture will not be any of these. It will be on satellite. Satellite cellism. You also have to, after
have been detected by observations of or change.
For example,
elevation
commonly
of the lake. So
glacier. You need all these sensors. You have to communicate this back to the Earth, and satellite.
Is rising up
You must think that the satellite will be 100 years.
and there are
And there TT down. If it can do that, so many satellites after a few years start wobbling. Why do they start wobbling? You must increase these particles are coming, they're hitting the satellite, all these surfaces. So satellite will start
delivering occasionally water. So they are draining out in outburst floods water. This is quite a new information about Antarctica, and has been collected only in the last few years, and by satellite altimetry and the satellite ICESat. And so this is a very exciting information that